Today we're going to build a full-fledged regular expression engine from scratch, the kind that underpins grep, sed, and virtually every programming language's regex library. This is not a toy, we'll support literals, wildcards, character classes, alternation, grouping, and quantifiers. The heart of our engine is Thompson's construction, which turns a regex pattern into a nondeterministic finite automaton, or NFA, and then simulates that NFA on a given input string. We'll write the whole thing. First we define the two fundamental pieces of any finite automaton, a state and a transition. A state has a unique numeric ID and a list of outgoing transitions. A transition stores a character symbol and a reference to the next state. We'll use a special convention. The null character 0 will represent an epsilon transition, a free move that consumes no input. The dot character will stand for any literal character, which we'll later use to implement the wildcard. Each transition carries exactly one character, but a state can have multiple transitions, allowing the NFA to explore several paths in parallel. This is the basic vocabulary our entire engine is built upon. We introduce a helper class called fragment. Every time we construct a piece of an NFA, say for a single literal character, we return a fragment containing a start state and an accept state. By keeping those two states together, we can later connect fragments with epsilon transitions without knowing their internal structure. The NFA class itself is just a thin wrapper around a fragment. It exposes a matches method that simulates the automaton on an input string. The simulation uses a set of current states, starting from the start state and following all epsilon closures. For each character of the input, it moves to any state that can be reached by a transition whose symbol matches the input character, or the special dot symbol. The simulation returns true if any of the final states after processing the entire string is the accept state. The parser class is where the real magic happens. It walks character by character through the regex pattern using a position index. The top-level method is parse, which calls parseExpr and then checks that we consumed the whole pattern. The grammar is described by three methods. ParseExpr handles alternation. It first calls parseTerm to get a left-hand fragment, then while it sees operators, it parses the next term and combines them via a union operation. ParseTerm handles implicit concatenation. It starts with an epsilon fragment, then repeatedly parses factors and concatenates them until it hits a closing parenthesis or the end of the pattern. ParseFactor handles quantifiers. It parses an atom, a literal, a parenthesized group, a character class, or a dot, then checks if the next character is, or, and wraps the atom's fragment with the corresponding star, plus, or optional construction. This structure gives us correct operator precedence. Star beats concatenation, which beats alternation, exactly like standard regex. Atoms are the leaf nodes of the regex grammar. ParseAtom looks at the current character and dispatches accordingly. If it sees an opening parenthesis, it recursively calls parseExpr for the inner group and consumes the closing parenthesis. If it sees an opening bracket, it calls parseCharClass, which builds a set of allowed characters, supports ranges like AZ, and handles negation with caret. If it sees a dot, it returns a fragment whose transition carries the special dot symbol. If it sees a backslash, it takes the next character literally, useful for escaping special characters. Otherwise, it's an ordinary literal character and we create a simple two-state fragment with a transition on that character. Character classes are expanded into multiple transitions, one per allowed character, all going from a single start state to a single accept state. This makes the NFA deterministic for that portion, but keeps the overall structure uniform. The parser relies on a small library of combinators that build NFAs out of smaller pieces. Make literal, C, creates two states with a single transition labeled C. Make dot, creates a transition with the special dot symbol. Make epsilon, creates two states connected by an epsilon transition. The parser relies on a small library of combinators that build NFAs out of smaller pieces. Make literal, C, creates two states with a single transition labeled C. Make dot, creates a transition with the special dot symbol. Make epsilon, creates two states connected by an epsilon transition. Star, frag, creates a new start and accept, adds epsilon transitions to go around the fragment, 0 times, or loop through it, many times. Dot, plus, frag, is implemented as concatenation of the fragment with its own star. Optional, frag, is a union of the fragment with an epsilon fragment. These operations are pure state machines. They don't depend on any textual representation, which makes them easy to test and reason about. Simulation of the NFA is the engine that actually answers does the string match. It maintains a set of current states, starting from the epsilon closure of the start state. Epsilon closure is computed by a depth-first traversal using a stack. From a given set, it finds all states reachable via epsilon transitions and adds them to the closure. For each input character, we look at all outgoing transitions from the current states. If a transition symbol exactly matches the input character, or if it's the dot symbol, we add the destination state to the next set. After processing the character, we take the epsilon closure of that next set. If at any point the current set becomes empty, the match fails. After all characters have been read, we check if the accept state is in the final set. This algorithm runs in worst-case exponential time for truly ambiguous patterns, but for most practical regex it's efficient. In our main method, we run a battery of test cases. Each test calls the matches static method, which creates a parser, builds the NFA, and simulates it. We test simple literals, A matches A, but not B, the wildcard. Matches any single character, the clean star, a matches 0 or more as, plus, or requires at least one, optional, A, alternation, CD, grouping with repetition, A, B, C, character classes, ABC, and AZ, and their negated versions, and combinations like H.low and Kalu, R. Each test prints the result and compares with the expected Boolean, showing a pass/fail indicator. This validates every feature we've implemented. We've just built a working regular expression library using Thompson's construction and NFA simulation. This is the exact same technique used in early Unix tools and in many modern regex libraries. By building it ourselves, we've seen how a declarative pattern language compiles to a computational model, and how nondeterminism is managed through state sets. You can now extend this engine with bounded repetitions, non-capturing groups, or even convert it to a DFA for guaranteed linear time matching. The core ideas you've learned are foundational to the whole field of automata theory and pattern matching.